In question number 69 of current in conductors, a 100 microfarad capacitor is joined to a 24 volt battery through a big 1.0 mega ohm resistor. So when you join it, the charge and the current in the capacitor starts flowing, and plot the qualitative graph between current and time for the first 10 minutes, between charge and time for the same period. So once we have a capacitor connected through a battery, something like this, the current starts flowing. Initially there is 0 voltage across this capacitor and this 24 volt here. So the current starts flowing like this through this resistor, trying to charge this capacitor. When the voltage on this capacitor starts increasing, let us say this is 24 volt, initially it is 0 volt. At some point of time there is a 4 volt voltage across this capacitor. So the voltage across this resistor decreases to 24 minus 4 or 20 volt. Initially it was 24 volt. Later on it became only 20 volt. When the voltage across this capacitor reduces, the current through this resistor reduces. At some more time passes, the voltage across this capacitor increases even more. So let us say it is 14 volt. Then the voltage across this resistance reduces to 24 minus 14 or 10 volt. So the current reduces even more because the voltage has reduced even more. When the voltage across this capacitor has become full 24 volt, the current across this resistor stops because the voltage on across its two ends are both the same. We need to find the plot of this charge in the resistor. We know that the charge on this, as the voltage on this capacitor starts increasing with the time, it means the charge on this capacitor is also increasing with the time, and the formula of the charge on this capacitor at any time t is given by Q is equal to Q V naught 1 minus e to the power of t by RC. And if we differentiate this one with respect to t, then we get I equal to dq by dt. The first term is constant, the second term is minus Q naught multiplied by differentiation of e to the power minus t by RC is e to the power minus t by RC multiplied by differentiation of this term, which is minus 1 upon RC, minus cancels, comes plus I is equal to Q naught upon RC e to the power of minus t by RC. Instead of Q naught is the final stable charge on this capacitor, which happens when the voltage across this capacitor becomes equal to the voltage of this battery, or we call it V naught, and that charge Q naught is given by CV naught. C cancels, it's V naught by R, and V naught by R is nothing but the initial surge voltage across this resistor. Let's call it I naught. We can calculate it as V given as 24 volt and R is given as 10 to the power of 6 ohms. We call it, if we take 10 to the power of 6 above, we can say it as a microsecond. So I am putting 24 as I is equal to 24 e to the power minus. It's good idea to calculate the RC time constant, and in this case R is 1 mega ohm and C is 100 microfarad. If you multiply these two terms, you get the time constant. The time constant here is R is 1 mega ohm, capacitor is 100 microfarad, 10 to the power minus 6 and plus 6 cancel out. We get 100. We can write 100. It is easy to look at the things in terms of the time constant t to make this calculation easy. We need to plot the graph of I with respect to t, and for that we make use of the time constant on the x-axis. We know that initially when t is equal to 0, I is equal to 24 microampere. E to the power 0 minus 0 is 1 upon e to the power 0, or e to the power 0 is 1. So that is why at t is equal to 0, I is equal to 24 microampere. And when t is equal to infinite, this is 1 upon e to the power infinite. E to the power infinite is infinite, and 1 upon infinite is 0. I becomes 0. So after a long period of time, the current becomes 0. And this is how the graph looks like. Initially, this current I has a value of 24 microampere. At time t is equal to infinity, as goes to infinity, this current tends to 0. At calculated at different point, we have to calculate it up to t is equal to 10 minutes, and 10 minutes means 600 seconds. So we calculate the value of I at different values of t: 100, 200, 300, 400, 500 and 600. At t is equal to 100, this becomes 24 e to the power of minus 100 by 100, or minus 1, or 24 e to the power of minus 1. So we get at t equal to 100, this is 24 e to the power minus 1. At t equal to 200, this is 24 e to the power of minus 2. At t equal to 300, this is 24 e to the power of minus 3, and so on and so forth. We can plot this one as a graph like an exponentially decreasing value of e. To plot the value of q with respect to t, we know that q is equal to q naught 1 minus e to the power of t by rc. Q naught is CV, C is 100 microfarad, V is 24 volt. 1 minus T by, we know that RC is 100. 100 into 224, we can also write 2400. 2400 and micro becomes 2.4 microcoulomb. We can use the same thing to plot Q at T is equal to 100, 200 and so on and so forth. When T is equal to 0, this thing is e to the power of 0 or 1. So q is 0. 1 minus 1 is 0. When t is equal to infinity, this thing becomes 1 upon infinity or 0. The whole thing is 2.4 microcoulomb. So initially the charge is 0 and finally it tends to 2.4 microcoulomb. In between, we can calculate the value of q at t is equal to 100, t is equal to 200, t is equal to 300. At time constants of RC, 2RC, 3RC and so on. So we get the value at t is equal to 100 or 1 time constant as 2.4 1 minus e to the power of minus 1. At t equal to 200, it is 2.4 1 minus e to the power of minus 2. As t is equal to 300, it is 2.4 1 minus e to the power of minus 3, and so on and so forth. So that is how these graphs looks like.